When you open a file on your computer, it feels instantaneous, right? A simple click. But behind that simple action, you're kicking off this incredible journey deep into the heart of the Linux kernel. So today, we're going to pull back the curtain and demystify one of the most common, yet surprisingly complex operations there is: opening a file. So here's our roadmap. First, we're going to talk about the magic of the VFS. That's the stage where this whole show happens. Then we'll follow the open call as it starts its adventure. Watch it navigate the file system path, see how the kernel forges a special object to manage the connection, and finally, we'll get to the prize our program gets back and talk about why this whole thing is so important. Okay, let's set the stage. Before we can even begin, we need to understand the world our little system call lives in. And that world is governed by a truly brilliant piece of engineering called the Virtual File System, or VFS for short. I mean, think about it for a second. This is really the core idea behind Linux. You can interact with a text file, a printer, or even a network connection using the same basic commands. How on earth is that possible? Well, the secret sauce is the VFS. Think of the VFS as the kernel's universal translator. It's this amazing abstraction layer that lets your program just say, open this thing, without having to know or care if this thing is on an X4 hard drive, an NFS network share, or a special device. Your app just speaks one language, and the VFS handles all the translation. All right, the stage is set. We know about the VFS. Now let's actually start the journey. And believe it or not, it all kicks off with one very familiar line of code. This right here, this is our call to adventure. This simple little function in our program is the trigger. It's what takes us from the calm, safe world of user space and sends us plunging right into the kernel's domain to get the real work done. The second our code hits that open function, the CPU performs what's called a kernel trap. It's basically a special instruction that flips a switch, moving us from user mode into the super-powered kernel mode. From there, control gets handed off to a function called do sys_open at 2. You can think of it as the kernel's front desk manager, taking our request and starting to organize everything that needs to happen next.
So we're officially inside the kernel. Now what? Well, the first big job is to actually find the file we asked for. And that means navigating the file system's path, piece by piece.
To find its way, the VFS relies on two key guides. First, there's the dentry, or directory entry. This is just a signpost. It connects a name you'd recognize, like home, to its technical location. And that location is the inode, or index node. The inode is the real prize. It's the data structure on the disk that holds all the metadata, permissions, size, owner, everything the kernel needs to know about the file itself. And you can see this process in action right here. The kernel is super methodical. It starts at the root, the single slash. It uses the root's inode to find the dentry for home. Then it uses the home's inode to look up the dentry for user. It's this little game of leapfrog, hopping from one inode to the next entry all the way down the path until it finally gets to our target, data.txt.
Okay, but what about a little plot twist? What happens if the path walk gets to the end and the file isn't there?
Well, sometimes that's exactly what we wanted, right? We might have told the kernel to create it if it's missing. This is where the VFS is really smart. If that final lookup fails, but it sees the create frag we gave it, it doesn't just give up. It pivots. It calls another function, VFS create, which basically tells the actual file system, like ext4, hey, I need you to make a new inode right here, with this name. It's all handled seamlessly. Okay, so one way or another, the kernel has located our inode on the disk. Great. But that inode just represents the file itself. It doesn't represent our program's connection to that file. For that, the kernel has to create or forge a brand new object right there in memory. Now, this is a really, really important distinction. The inode is the one permanent record of the file on disk. But this struct file, it's a temporary object that represents a single session with that file. So if two different programs open the same document, there's still only one inode on the disk, but the kernel creates two totally separate struct file objects in memory, one for each program's unique session. And this new object is like our session's control panel. fpath links it back to the inode we found. fpause is like a personal bookmark, keeping track of exactly where we are in the file. And fop, that's a pointer to a list of functions, the specific toolkit for how to read, write, and interact with this particular type of file.
And this is the magic moment where it all clicks into place. A function called doDentryOpen comes in and makes the final connection. It takes that affop pointer in our new struct file and hooks it up to the specific functions from the underlying file system. And just like that, our generic file object is now a fully operational, customized connection ready for I/O. So, after all this incredibly intricate work inside the kernel, the path walking, the lookups, creating this new object in memory, what does our program get back for all its trouble?
It gets a number. That's it, a simple integer. After everything we just saw, the grand prize is a number, like 3.
This number is everything. It's the program's magic ticket. From now on, the program doesn't need to know about paths or inodes or any of that kernel stuff. It just hands this file descriptor back to the kernel and says, hey, write to the file for this ticket, and the kernel knows exactly which struct file to use.
So you might be thinking, okay, that's cool, but why? Why build this incredibly complex, layered system just to open a file? Well, the payoff for all this complexity is absolutely huge.
This abstraction is basically the superpower of Linux and systems like it. It means programmers can write much simpler code that works everywhere. They don't have to worry about the specific hardware underneath. It's this decoupling that makes the whole system so powerful, so flexible, and so robust.
And this quote from the kernel's own documentation just nails the philosophy. The interface that we as application developers see, that open function, it's rock solid. It almost never changes. But because all that complexity is hidden away, the stuff underneath, the VFS, the drivers, can constantly be improved and optimized. So the next time you open a file, just take a second and remember this incredible, invisible journey that it kicks off. That one simple action is a testament to one of the most powerful ideas in all of software, hiding complexity behind a simple, beautiful interface. The VFS proves that the best systems aren't just about what they can do, but about what they allow us not to have to worry about. And that really makes you wonder, what's the next big, complex part of our world that's just waiting for its own version of a file descriptor?